Where the momentum idea really starts to shine is when you get into Newton's third law, which can be quite confusing in the viewpoint that we've done so far. It really cleans up a lot in the momentum idea, and also not only does it clean up, it becomes much more powerful and important and becomes one of the real driving principles behind how we think about how the world works. So remember that in the old viewpoint, what we said for Newton's third law was basically that if object A exerts a force on object B, then that means object B is also exerting an equal and opposite force back on object A, which had all these crazy consequences that we kind of tried to wrap our head around in some of the previous parts of the course. Now, what does that have to do with momentum? Recall that from Newton's second law, we know that F delta T is delta P on average. So if forces exist in equal and opposite pairs, the delta T is not going to have any influence on this conceptually. So if the forces exist in equal and opposite pairs, doesn't that mean that changes in momentum also occur in equal and opposite pairs? That is the interpretation of Newton's third law in the momentum viewpoint. So changes in momentum occur in equal and opposite pairs. If object A's momentum changes, then object B's momentum must change by an equal and opposite amount. This principle is referred to as conservation of momentum. And I'll explain why in a couple of minutes. So first, to understand what I'm saying here, what I'm saying is that if the motion of one object changes, then there must be another object somewhere whose momentum has changed by an equal and opposite amount. So if the motion of one object changes, it means there must be another object somewhere whose momentum changed in the opposite way. So for example, like going back to some of the things we talked about earlier in the course, let's say like, you know, a batter hits the ball in baseball. The ball's momentum changes because of that. What I can say is, well, if the ball's momentum changed, then there must be another object somewhere, namely the bat, whose momentum changed by the same amount in the opposite direction. Or like in the case of recoil on a gun, the bullet's momentum changes when you shoot a gun. So therefore, the gun's momentum must change by an equal amount in the opposite direction. And that would be your explanation of why guns recoil. Because the gun's recoil is going to be exactly the same amount of momentum as the bullet's forward momentum that the gun gave it. So anytime one object imparts momentum to another object, it has to absorb the same amount of negative momentum, basically. Another way of saying this is that one way to think about this conceptually is that the total amount of momentum, you have to think of momentum as a vector for this to make sense, but the total amount of momentum in the universe never changes, because anytime momentum is created in one direction, the same amount of momentum is created in the opposite direction. So in the grand scheme of things, if you think about everything in the universe as being part of one unified system, the momentum of that system can never change. Because if one part of the system gains momentum to the right, another part of the system is going to gain momentum to the left. If one part of the system gains momentum upwards, another part of the system has to gain momentum downwards. And the really cool thing about this is we can make these statements without knowing anything about the forces involved. These could be the forces we talked about so far in the course. They could be completely different forces that are really hard to understand and really abstract and involved. Doesn't matter what the forces are. No matter what the force, no matter how complicated, it has to obey conservation of momentum. So if you see an object move, it must mean another object moves in the opposite direction. And this turns out to allow us to solve some really difficult problems in a really simple way, because without knowing anything about what's actually going on in the problem, we can already say, like for instance, a simple example is that example of shooting a gun. You can know nothing about how a gun works, what's the chemical reaction that goes on inside of a bullet. There's some kind of chemistry involved in creating a little explosion that shoots the bullet out of the gun or something. It doesn't make any difference. All you have to know is the gun gives the bullet momentum forwards. That's enough information already. If I know how fast the bullet is coming out of the gun, I can already tell you the rest of the physics, because if I know the speed of the bullet coming out of the gun, I can tell you the speed that the gun will recoil backwards, because the momentum changes have to be equal and opposite. And that's the really powerful idea. Now, why do we call it conservation of momentum? This is a term that's going to come up a lot for the rest of the course. Conservation in physics is when something never changes. Another way that people often say that is, it is impossible to create more or to destroy some of that thing. The total amount always remains the same. So in this case, conservation of momentum, that's the exact statement I was just making. Conservation of momentum means that the total amount of momentum can never change. You can't create momentum in the grand scheme of things. You can create momentum in an object, but then that will cause you to create another momentum somewhere else that cancels that out. So in the grand scheme of things, you can't create momentum. Really, you can just exchange it around, move it around and manipulate it, but you can't actually make more. You can't actually push something forward without an equal and opposite reaction to that. It will encounter another conservation principle a little bit later on in the course. But first, let's get a little bit more involved in how you deal with conservation of momentum.